Before we continue with glycol dehydration, I forgot something here. It is what we call hydrate. Hydrate is water which is become like rock. So if it is occur in a pipe, it end up with having plug the pipe. So usually the problem is in the low pressure and low temperature. You see here, this is the boundary for the hydrate. So hydrate formation line, this hydrate formation line. So if you end up with having a low temperature, which is usually is see, this is around 30 degree Fahrenheit, so 35 degree Fahrenheit, and low pressure also, you end up with having a hydrate, which is we don't like to happen in our pipeline. So what happened here usually is happen in area which is in the North Sea, in the Gulf of Mexico, probably, but Gulf of Mexico is hot enough, not as cold as the North Sea, or in Alaska probably, but it will not occur in Indonesia, which is it's rarely we have a 20 degree Fahrenheit or 30 degree Fahrenheit. Usually it's around 80 or something. Even in water, it's not up to that number. So that's why for formation hydrate formation is it's not important in Indonesia. Okay, let's continue with the glycol. Let's do it problem. It's much easier for us to problem. For example, that we have a reservoir and temperature and pressure is around 4,000 pressure psi, and pressure and temperature is 320 degree Fahrenheit. The rate is 19.5 million cubic feet. With the solid brine is around 3.75 degree percent, and the gas density is 1.3, which is quite heavy. Mole fraction is to SE 10%, and 15%, so 0.15, 0.1, and 0.15. We calculate the water content by using figure 25, and because figure 25 is for a larger temperature, so we use figure 25. If you want to see it, so you can see that the difference between figure 20 and 25 is just the temperature here again. So this is temperature until 400. This one is only 280, more, a little bit about it. So temperature is higher in figure 25. So 25, and then we come up with the CG of 0.88, and a correction for solid content is 1.914. So the solid content is 1247. So if we see the figure 25, you see that we have 320, and with the 4,000 psi we have a 1,550 of 1 mass million cubic feet, and we correction of 0.88 with around 320, and this one is with the brine of around 3.75, so we end up with being 0.917. Okay. Go back to the first slide, and so we have a water content of corrected of 12.7, but we continue with the impurities. we will use the method number 3. So if we calculate this one, 0.1 plus 70% of 0.15, we end up with having 0.205. Of 0.205, and if we see on the figure 2015, we have 1.3 of water content ratio. Let's go to figure 2015. So we have 320 degree Fahrenheit with a little bit 20 point something, and then goes to up a little bit more than 20 with the 4000 psi. We end up with I think 1.2, 1.1, 2, 3, 1.3. Okay, if we go 1.3, so the water content is 1246.48 multiplied by 1.3, so become 1621. Okay, so the water mass rate is this water content multiply the flow rate, so it's become a mass rate. So the mass that coming to the scrubber. Okay, so after the scrubber, the pressure is become lower, and also the temperature become lower. From 4000 become 1000, from 320 become 120. And again we do the same thing for this one. 105 the water content with the CG of 0.958. Okay, and then CS1, because why? I assume that there is no what you call it, solid content. It's already been in scrubber, it's going out in scrubber, so I assume this S1 because there is zero solid content, and this one become water content. Let's go to the figure 25, because we use figure 25 also. Figure 25 in slide number 8. Okay, you see that 120. Okay, and then the 1000 psi for this line, and we end up with 105 pound mass per million cubic feet. And if you see that correction is for the same 1.3 of gravity of a gas with 120 psi degree Fahrenheit, go to the left, so we end up with having 0.9958. Okay, and for this one, since we have no solid content, so we assume that it's being it's going to scrubber is empty, so it become 1 in the correction. Okay, for salinity. Okay, and then this is assumption also. Usually we still have a salinity, and then go up. See what we have here. See, okay, so we have a 0.958, so we have 101 pound mass per million cubic feet. So we're going to figure 20.5 with 0.205 or pseudo H2S mole fraction. Okay, and then we see what happened here. So if you see 120 degree Fahrenheit with around 20.5 something, go up, and then to the left we end up with having 1000 psi, 1.1 of water content ratio. So we goes to water content ratio 1.1. Okay, and the water content is 110. So the mass rate is this 250 pound mass per day. Remember that if you okay, we calculate pound mass per day, so just multiply by flow rate. Means that actually we at first we have almost 32,000 pound mass per day. We have only 2,200 pound mass per day because of the reducing the pressure and temperature. So actually it's going up to scrubber. Going up to scrubbers is around 29,000 pound mass per day. So it's a lot. So a lot more is going to scrubber, going up to scrubber. So this C here is coming to the glycol dehydrator, dehydrator. So A is left, scrubber going up water. So this one is the one that going to dehydrator. Okay. So we almost finished. So water content specific gas cells is 7 pound mass per million cubic feet. Usually it's a setup. We have to have this number, otherwise we cannot sell anything. So if, we will continue for the DEF for the next video.